Ang tatlo lang kayong maglalaban. Dapat siguro may ano ako, may plus point sa exam pag yung lab section nyo ay laging nasa nasa podium. We'll start 11:05. 05. One L, 2L. Walang 8L? Walang sumasali na 8L? Last 2 minutes. Mag-start tayo. Okay, get ready. Six questions. Okay, start. Okay, so the correct answer is asynchronous. So the main requirements for a solution to the critical section problem are first mutual exclusion. Progress would mean that no process will the system will not deadlock, will not be in a deadlock state, and bounded waiting means that a process will not starve or will not wait forever. Wait. Okay, CD4L. Okay, so the correct answer is task struct. Okay, because task struct is the data structure used to represent a PCB in Linux. Okay, and it's actually also used for creating threads using the clone system call. But Kthread, Ethread, and TEB are all under Windows. So the correct answer is task. Okay, CD7L. Okay, so the correct answer is true because when you fork, okay, so let's say a process has many threads and then that parent process calls fork, and then what will happen is if the exec call is made after the fork, then the child process will be overwritten by the new program, which is the parameter in the exec system. So the correct answer is true. If you don't call exec after the fork, then there might be some problem, okay? Or not a problem, but you need to decide whether the threads will be inherited by the child process. Case 2L, currently 4. Okay, is the count variable, okay? Because uh, the count variable is incremented by the producer process and decremented by the consumer process. So the other variables are just for marking position of the uh, position on the buffer. Okay, next question, still from 2L. Okay, so the correct answer is sig int. Okay, sig term and sig kill are used to terminate a process. Kill using the default kill, you send a uh, sig kill signal to a process. Kill -9, that is -9 is sig term, force terminate. Sig hop is hang up. Okay, press Control Z, I think. Okay, so the correct answer is sig int, and you can override this by writing your own signal handler. All processes in Linux by default has a default signal handler for some of the signals, but you can override some of the signal handlers by writing your own signal. Okay, 2L. Last question. Okay, the correct answer is Peterson solution. Peterson solution is a software solution for two processes. Okay, two processes only. The others, test and set, compare and swap, and interrupts are all hardware solutions because they have specific instructions like XCHG, exchange instruction in the x86, right, for the compare and swap, and I forgot the other one for the test and set in x86. And of course, interrupts, you have CLI and STI. Okay, so the winners for today's quiz are the following. Aaron from 7L. Perpignan from 5L. Yeah, my lab section. And Kulaway from 2L. Congratulations, everyone. So great. So it means that some of you are really studying. Okay. For some announcements, the exam is moved to Tuesday after the reading break, and please study the same coverage. So I guess we'll just be making some adjustments on the schedule of the exams because we're running late. Okay, so let us continue our lecture. So we're currently looking at some of the tools, synchronization tools for cooperating processes. And our model problem is the producer-consumer problem, specifically the bounded buffer solution, wherein you have a limit on the number of items that you can place on the buffer, and you have the producer thread or producer process that writes something on the buffer, and then you have a consumer process that reads something. And we've discussed some of the techniques, like the hardware techniques that were presented in the previous video. So today we're going to continue with Mutex locks. The idea of introducing this Mutex locks is that somehow it provides an easier way for application programmers to write, to provide solutions for the critical section problem. although we can abstract, in the previous discussion, we have the abstraction of test and set and compare and swap, but underneath it, you still have to basically use the name test and set and compare and swap. So again, to make it easier, they introduced the abstraction of lock. So why don't we just call this approach as locks? Okay. So the simplest one is called the mutex lock, okay? And it's basically a Boolean variable which indicates that a lock is available or not. And to protect a critical section of code, first you have to acquire a lock, and then after the use of, or after the execution in the critical section, you release the lock. Okay? And the main requirement for the mutex lock is that the acquire and release should be atomic. Again, they should not be interrupted when they are executed. Okay? And actually, to implement these mutex locks, you still have to go back to the low-level implementation or low-level instructions like the compare and swap. So you can think of mutex locks as just an abstraction or a wrapper on the low-level hardware solutions. Okay? And however, the mutex locks requires what we call busy waiting. So it's busy waiting would mean it's just a loop that jumps. It's a continuous loop. So when you have a jump to itself, to itself, okay, to a location in memory, then basically that's called busy waiting, and it eats up CPU cycles. So that's why it's called spin lock. So you can think of the lock like this. So you have a loop that continuously spins, okay, on itself, jumps to itself to location. It's called spin lock. Right? And here is the solution to the critical section problem using lock. So first, you acquire a lock. Okay? So once you have the lock, then you do the critical section and then you release it. So it's like going to the CR. Okay? So first you acquire the lock and then do your thing. Critical section is what you do in the CR, and then you release the lock and then you get out. That's basically the idea. So it's simpler, right? Because you simply have to call whatever these functions are. In the case of p threads, in the previous lab, you have p thread mutex lock, right? And signal and wait. So those are so that's mutex locks. I will not show an example, but it's actually in. I have this in the. Later, I will show an example for after the lecture. Okay, so that's mutex locks. Very simple. The next one is a semaphore. Okay, semaphore are synchronization tools that provide more sophisticated ways rather than just mutex locks. Okay, and it's at a high level, you can think of semaphore as just an integer variable. Okay, and you define two operations on the semaphore. The first one is called the wait, and the other one is the signal. So originally, it's called P and V. Forgot the why it's called P and V, but the wait and signal, they were originally called P and V. And the wait operation is implemented like this. So you have the integer s, which is the semaphore itself. Then while s is less than or equal to 0, right? So this is the busy waiting. So it does nothing. Checks the condition false or true, okay, then spins this area of the code. Then otherwise, you decrement the value of the semaphore. Now the signal is opposite, the opposite operation. So you simply increment the semaphore, the value of the semaphore. So that's how it's done. How the semaphore is implemented. There are two types of semaphores. We have the counting semaphore, wherein the integer value can range over an unrestricted domain. So you use semaphores actually when you have a resource with several instances. So say you have a disk and then you have several disks, right? So you can use a semaphore for synchronization. So that's counting semaphore. Binary semaphore, the value of S can range only between 0, between 0 and 1. Right? So it's a binary semaphore, and you can actually treat it as similarly just like a mutex lock. Right? So 1 would mean it's locked, 0 would mean it's unlocked. So you can actually use binary semaphore and treat it like a mutex lock. Okay? So you can implement a counting semaphore S as a binary semaphore. With semaphores, we can solve various synchronization problems. So here's an example of the use of a semaphore for solve two examples. The first one is solving the critical section problem, wherein you create a semaphore. You name that semaphore mutex because it's a binary semaphore, and you initialize that to 1. And to solve the critical section problem, simply call wait on the mutex, which is a binary semaphore, and then signal mutex, wherein mutex is a binary semaphore. Right? You can also use semaphores if you want to synchronize the operation of two processes, meaning you have two statements that you want to be executed one before the other. So consider you have two processes P1 and P2 that will with two statements S1 and S2, and the requirement is that S1 should happen first before S2. So what we can do here is to create a semaphore called sync and initialize it to 0. And in process 1, we call S1, and then since we want S1 to happen first or to be executed first before S2, right? So in P2, we wait for the semaphore, and then on process P1, so initially it's set to 0. Okay, so on process P1, after performing statement 1, we signal the semaphore, and then it is only after signaling that process 2 can execute S2. So that's the idea of another example of the use of semaphore. Okay, so have an example. Use let me check. So our model problem is the producer-consumer problem. So in the repository, we have several examples, several versions of the producer-consumer problem implementing the different synchronization primitives. So let's look at ProdCon SEM. So this is a solution to the producer-consumer problem using semaphores. Okay? So let's take a look at the code. So here we specify multiple threads, multiple number of producers, and multiple number of consumers. So we have a preprocessor directive that tells us how many producer and consumer threads are we going to create. and then the iteration for the producer and the iteration for the consumer. Then we have the thread functions. So we have the buffer, the in and out variables. So here you can see that we're using sem_t for the mutex. So remember that we can actually use semaphores to represent or for use as for mutual exclusion. So we have something like this. Then we have it's actually a counting semaphore that tells us whether there are still slots in the buffer. Okay? So we have semaphore for full and semaphore for empty. Okay? So counts the number of empty slots and counts the number of filled slots. So here we create an array of producer threads. We define an array of producer threads. Then we initialize the random number generator. And then here, this is where we initialize the semaphores. So the mutex will simply be used for 1 or 0. So we initialize it to 1. Okay? Then for the full, since this is the start of the process, no items yet, so we have 0. And for the empty semaphore, we have buffer size, meaning all buffers are still empty. This is the initialization part. Then we have a loop that spawns the thread, that actually creates the thread. Okay. Then here we pass to the thread, the process ID, the thread ID, producer ID in this case, and for the consumer we also do that. Then we join the threads. And let's take a look at the producer code. Okay. So at the producer code, of course, we loop for a number of iterations, and then we produce the number, and then this is how we use the semaphore. Okay. So we wait for an empty slot to be available. Okay. So we have some wait at address of empty, and then once a slot is available, okay, we use the mutex to make sure that we are in the critical section, because we are actually accessing buffer and the in where we're changing this. Okay, so we place the item produced on the buffer, and then after doing this, after updating the buffer and in, we now post the mutex, okay, and then post full, okay, meaning that okay, another item is available. Okay, so the opposite is the same with the consumer function is the same, the opposite. So prod con semaphore. This is the what will happen. So several consumer threads and one producer thread will access the buffer, and if you observe the code, see the events that are happening, the items that are being produced. So you can check this out and study the code on how we used semaphores to synchronize the producer and consumer process. Okay, so that's the idea. So how do we implement the semaphore? So the basic implementation of semaphores is like this. Okay, so this is the basic implementation. So this one. Now, again, the problem with this is First, we must guarantee that no two processes can execute the wait and signal on the same semaphore at the same time. So the implementation is also a critical section problem, right? And we can also have, we now have a busy waiting, the critical section implementation, okay? But if the implementation code is short, so the implementation code is short, okay? So this just block, this block, okay? So these are, so remember that, okay? S minus minus and S plus plus. That's very similar to counter plus plus and count minus minus, which is actually can cause a race condition. Okay? So that's why the wait and signal should be implemented atomically. Okay? So the main issue is actually busy waiting. But if you have a single processor, okay, the standard implementation will work. Okay? But if a lot of applications spend a lot of time in the critical section, then the basic implementation of semaphores will not be sufficient. So a better solution is to implement semaphore with no busy waiting. Okay. So when you say busy waiting, the CPU is still busy performing jump instruction. Basically, that's what we mean by busy waiting. Jump to this location, same location, then jump to itself. Okay. So the problem with that is, yeah, it's inefficient for some applications that has a very large critical section. Okay. So one solution to achieve this with no busy waiting is to have each semaphore to have an associating waiting queue. Okay? And each entry in the waiting queue has two data items: the value of the semaphore and the pointer to the next record in the list. So you have a data structure, a list basically. And the two operations, you have two operations, block, which place the process invoking the operation on the appropriate waiting queue, and wake up, which removes one process in the waiting queue and place it in the ready queue. So in this implementation, we now have context switching. In the original one, we don't have context switching. So the CPU is executing a jump instruction, which is actually somewhat useless. Okay? So here we have a context switch. Okay? So this will be the waiting queue. Okay? The implementation as described in the previous slide. So on this semaphore, we have a list of processes waiting on this. And the wait implementation will look like this. So this is now okay. The semaphore now has a value and a list of processes. Okay? So first, you for the wait, you decrement the value of the semaphore, and then if the value is less than 0, okay, the process that invokes the wait on the semaphore, okay, will be added to the S list, and then this process will block. Okay? So block is a system call, okay, which switches the state of the process from ready to waiting of the block system call. And so that's essentially what happens. So you don't have as you can see, there is no while loop. So that's the main difference, to differentiate the one with busy waiting and the one without busy waiting. In the one with busy waiting, this while loop is the one that performs the busy waiting. Whereas here, you don't see any loop here. So you call the system call block, and then you call the system call wake up. So there's a context switch that happens, and this is how the code will look like. So we presented two implementations of semaphores. Basic one with busy waiting, and this one without busy waiting, but uses the block and wake up system calls to change the state of the process. So problems, what are some of the problems with semaphores? So this is a somehow a programmer primitive, a low-level primitive, but somehow higher than the hardware. So you can think of this the hardware solutions as the low level, and then the next level will be semaphore. Now, since it is left to the programmer to use this primitive semaphore primitive, it's possible that the programmer might commit mistakes when writing his program. Probably you've encountered this in implementing the solution to the dining philosopher's problem. So one possible mistake would be to reverse the process. Okay? So you call signal first before you call wait. So the normal process would be wait and then signal. Or you did not use signal at all. So during the first call, you have wait, and then you have a second call waiting on the same mutex or semaphore. There's a problem. So basically, you have a hanging process. Okay? Then actually omitting the wait and the signal. So you forgot to use the wait and signal, okay, for some unknown reasons. So these and others are examples of what can occur when semaphores and other synchronization tools are used incorrectly. So a solution again is sa ComSci, alam naman natin na to make things easier, we try to make things easier for the programmers, for the user. But the so in this case for synchronization primitives, okay, using the plain semaphores for synchronization can cause a lot of problems. Why don't we problem sides switching? Okay. So why don't we introduce another abstraction? And this abstraction is called monitors. Okay. Let's not let the programmers call the wait and the signal themselves. Let's just use this monitor. So a monitor is a high-level abstraction that provides a convenient and effective mechanism for process synchronization. The best example that you can talk about is the synchronized keyword in Java. Okay. If you want a method, right, to be executed in a monitor, you prefix that with a modifier synchronized. So that's the idea, and the programmer doesn't need to do anything about synchronization. It will be guaranteed that that function will execute uninterrupted inside the monitor. So it's an abstract data type. Internal variables are only accessible by code within the procedure, method, or function, and only one process may be active within the monitor at a time. So it's like an isolation room, okay? And the syntax, pseudocode for the syntax will look something like this. So you define a monitor abstract data type, okay? And you specify the name of the monitor. Then you have the functions that will be executed inside the monitor. And these procedures can access only these functions can access the shared variables inside the monitor. Think of this as an abstraction, an isolation room. Okay? So this is a schematic view of a monitor. So basically you have, as I said, you have the isolation room, you have the shared data, and you have the functions, methods, operations that can only be invoked or you called inside the monitor, and some initialization code. And the processes or threads that would like to call these operations will have to get inside the monitor. It is only by then that they will be able to call this operation. The idea. So it's somehow the programmer doesn't need to think of calling wait and signal for the semaphore. So define for the programmer. Okay, I want this code to be executed or to guarantee mutual exclusion. Right? The programmer will simply define a monitor. And in the case of Java, it's even much simpler. You don't have to define any monitor. It's the Java runtime environment that creates the monitor. As long as you prefix the method with synchronized, it will be placed here. So in terms of Java, all synchronized methods will be placed in this isolation room. Okay, so that's the idea. And only one class or object will be able to invoke that method. Okay, atomically. So that's the idea of monitors. It's quite easy when you program in Java. You don't for example, in your project, say 22 probably, you did not call wait and signal. Simply call them, specify the method. Okay, this method will update the position of my character on the screen. So I will just place synchronized here so that the variables, the position of the character will not be messed around by other threads. Or that's the idea. Now, looking at the low level, okay, so let's define a monitor, an abstraction, but how do we implement that at a low level? So obviously, we still go back to the lower level primitive. So if you want to implement a monitor, we can actually implement a monitor. We implement monitor using Semaphores. So a lower level primitive. So it's very important in computer science that you learn how it works. So you start with low level, the abstractions, right? So you have to start with low level, like the test and set and compare and swap. And then we decided, okay, let's create semaphores. Okay? But to implement semaphores, we still need to use the hardware part, right? The hardware solution. And then okay, semaphore is problematic. Why don't we implement monitors? Okay? But to implement monitors, we still use the primitive type or the primitive solution, which is the semaphore. So that's a very interesting idea in computer science. So increasing the levels of abstraction. Anyway, that's just a side discussion. So we have to implement monitors using semaphores. We need to define two variables. We have the semaphore mutex and then initialize it to 1. And then each procedure, I don't have an example of this. I'll implement this later. So the procedures or the functions will be replaced by this. So this is the original function. You sandwich that in the wait and the signal operations, and then yeah, you have the monitor, quote unquote. But again, at the low level implementation, it's still the use of the semaphore. Now, okay, we were able to guarantee, using this basic implementation, we were able to guarantee that there is mutual exclusion, okay, inside the monitor. Now, that might not be sufficient to implement some other synchronization operations. So we need to introduce the condition variables. Okay? So we define them as a condition x and y, for example, condition variables. And there are only two operations allowed on these condition variables. So we have the weight and we have the signal. So the fact that you can see weight and signal, what will come to your mind is that probably is another implementation would be semaphores. Okay, so in the weight on the weight function on the condition variable, a process that invokes the operation is suspended until x dot signal is called. Okay, and x dot signal resumes one of the processes, if any, that invokes x weight. Okay? And if no x weight on the variable, then it has no effect on the variable, on the condition variable. Right? So this is how it will look like. Right? So okay, we were able to guarantee mutual exclusion in the monitor. Have a queue outside, then inside, well, inside the monitor, we might also want conditions to be satisfied first to be able to proceed the execution. So we introduce the additional queues actually on the by introducing what we call condition bar inside the monitor. Okay, so that's the idea. Queuing outside is not enough. It's quite limited. So why not do a queuing inside? You can think of this as a restaurant. So you have the monitor as a restaurant, and then you have a queue outside the main restaurant, and then condition variables. You can think of this as the CR. So while you are inside in the monitor, right, you don't have to go out to go to a CR. You can go to the CR inside the restaurant, right? And but it's possible that you may need to queue also in the idea of. And okay, so this is an example use of a condition variable. Remember that we are running inside a monitor. So consider P1 and P2 that need to execute two statements S1 and S2. And the requirement is that S1 happens before S2. So this is the same problem introduced earlier when how to use the semaphore. Okay, so using monitors, we create a monitor with two procedures F1 and F2 that are invoked by P1 and P2. So we have a monitor with F1 and F2, and then we define one conditional variable called X initialized to 0. Then we have another Boolean variable done. So again, this is a function in the monitor, within the monitor, and this is called by P1, okay, and this is called by P2. So what we're doing here is, okay, we have two processes. We would like to make sure that S1 gets executed first from process P1, and then S2 to be executed next only after S1 is done, which is invoked by process P1. So this will be the mechanism if we use the monitor construct. Okay? So inside the function in the monitor F1 called S1, we set that to true, and then we have the condition variable X. We signal that. Then in F2, again, F1 and F2 are, you might be confused. Okay? This is F1, this illustration, this is F1, this is F2. And then, let's say this is process P1, this is process P2. Okay? So process P1 will invoke this, process P2 will invoke this. That's the idea. Okay, and then For the F2, if done equals false, you simply wait on the condition variable and then you perform statement 2. So there is the use of condition variable to synchronize two processes. Monitor implementation using semaphores. Okay, so as I mentioned a while ago, okay, so we still go back to the semaphore as the primitive for implementing monitor. So to do this, we need the Mutex semaphore, next semaphore, and a next count, which is the number of processes waiting inside the monitor. And then each P will be replaced by, this was shown earlier. So you have wait, it'll probably show you. Okay, so this is the basic implementation. And this is another implementation. And the idea is you have a queue of processes. You use the next count to mark, to specify who will enter next in the monitor. Okay? And for the condition variables, okay, yeah, you have semaphore, which is the condition variable xsem set to 0. Have the x count. Then for the wait operation, this will be the implementation. So remember the one here. This is the wait call, and this is how that will be implemented using the semaphores. Okay. And then this is for the signal. Okay. That's the idea of implementing monitors using semaphore. Okay. This one with the condition variable. Okay, so I hope that's clear. Okay, okay, resuming processes within a monitor. Okay, so if several processes queued on condition variable x and x.signal is executed, which process should be resumed? So this issue will happen because let's say you have this condition variable x, okay? Then you have a queue of processes here, right? And then x.signal is invoked. Now, if you have x.signal, which one of these processes in the queue will be activated, right? So that's the issue being addressed in this question. So the first approach is first come, first serve, right? So whatever process is in the head of the queue, this FCFS, this will resume first because this is the first in the list, right? But that may not be sufficient, right? Because of some things or some events happening that might invalidate the reason or the condition why a particular process is waiting on that condition variable. So a solution is to use a condition wait construct, the form of instead of just plain wait operation, specify a condition which is actually a priority number, an integer, and the process with the lowest number indicates a higher priority and is scheduled next on the monitor. So that is the idea. So an example would be, okay, so a single resource allocation. So let's say, so let's use monitors, okay? to manage or to allocate a single resource. Let's say a printer, for example. So only one process can print on the printer. So what we do is to, let's say we have a single resource, okay? So let's say let's call this a printer. And we're using priority numbers that specifies the maximum time a process plans to use them. So R is the monitor, okay? So R acquire T, okay? So we have the acquire function and we specify the time that the process will use the printer, then print, then release the printer, okay? Where R is an instance of the type resource allocator, which is actually a monitor. So that's the use case, or how we're going to use the monitor to allocate a single resource. You can leave if you're watching this. You can leave. I will continue. I will finish this chapter. Just watch the remaining parts later. Okay, so this is how it's done. So to implement that resource allocator, so this is how we use the monitor. And for the resource allocator monitor implementation is how we do that. So this is the acquire function and the release function inside the monitor. And if BC, okay, so you have the time parameter here. If BC, okay, wait, okay, then set to BC true, okay, then release, okay, we set BC to false, then signal. And the initial code is that the BC is not false. So this is how it's done using monitor. So all processes that would like to print, okay, will have to call r.acquire this way, okay, and specify how long are you going to use the printer. Then you cannot print, okay? So this is the part wherein the process will print. You cannot print until this step returns, okay? So that is the idea of okay. So using that approach, okay, the way to use the monitor is first acquire and then release. Okay. Now, as you will observe, this is the similar problem. A similar problem will happen because this is exactly how the problems in the semaphore approach came about. The incorrect use of the functions. Okay? The ordering, for example, call wait first or signal, etc., etc. So the same problems here. So you release and then you acquire, acquire, and then omitting the acquire and release. So exactly the same problem. Okay? So how do we do that? We need to do some checks. So need to do some checking in order to guarantee that the proper ordering is actually done. But it's actually much simpler. Using a monitor is simpler than using the semaphore. Right? So that's those are the main topics for that for the higher level abstractions. For synchronization, we have Texlac, semaphores, and monitor. Now let's talk about liveness. Processes may have to wait indefinitely while trying to acquire the synchronization tool, the lock or the synchronization tool. Okay? Waiting indefinitely violates the progress and bounded waiting criteria. And liveness refers to the set of properties a system must satisfy to ensure that processes make progress, okay? And indefinite waiting is an example of a liveness failure. So the idea of liveness is parang buhay ka, okay? So kung buhay ka, you're making progress with your life. So parang kung wala ka namang ginagawa, tapos wala kang magawa, parang senseless na buhay ka pa. Parang ganun yung idea ng liveness approach. So similar to real life. So you have to make progress, and in OS, processes need to have progress also. Okay, so there are two things about liveness. The first one is called a deadlock. So deadlock is two or more processes are waiting indefinitely for an event that can be caused by only one of the waiting processes. So an example of this is the problem on the dining philosopher's problem. Right? So we'll discuss, you know this already, but the idea here is you have five. I will introduce the problem. So you have five philosophers here, and they have chopsticks or whatever. And the idea of a deadlock is the philosophers will need two chopsticks or spoon and fork to be able to eat. Okay? But what if simultaneously they pick the chopsticks on the left? Every philosopher pick the chopsticks on the left. So, and they're waiting for the other for the let's say this philosopher Tasio here already got this chopstick, but Plato here got this chopstick. So Tasio will wait for Plato to put down the chopstick in order for Tasio to eat. So the same thing happens to the rest of the philosophers. So that's actually a deadlock. Okay. So there are several conditions that will we need to characterize for about deadlocks, but we'll discuss that later. So here we have an example. We have two processes. An example P0 and P1. So here we have wait S and wait Q, and then signal S and signal Q. Now, as you can see here, this is wait Q and wait S. So this construct here will actually cause a deadlock. Okay? So that's a problem, and we need to address that. We have several approaches to address that. Another one is starvation. So the deadlock will happen if you are not making progress. Okay, so deadlock happens if the process is not making progress. In the case of the dining philosophers problem, they are all waiting for the chopstick, so they are not making any progress. They are not able to eat, so they will die actually. Okay? The other one is starvation. Okay? Starvation is indefinite blocking, meaning some of the philosophers will be able to eat, but there is one philosopher who will not be able to eat. Okay? So the idea here is a process may never be removed from the semaphore queue on which it is suspended. And the last one is priority inversion, scheduling problem when lower priority process holds a lock needed by higher priority processes. So you have a low priority process, then and it is not being released immediately, and a higher priority process will need that lock. That's a problem. So usually you have to define what you call a priority inheritance protocol. Okay, so that's liveness, and that's the end of chapter 6. Okay, so in this chapter, what we did is what we studied are some of the synchronization primitives or tools that can be used when we have processes running concurrently, either simulated or through parallelism. We can synchronize them. Okay, so that will be all for today. See you on the